This is a recorded presentation of using digital tools from the U.S. Geological Survey and the Federal Highway Administration to address water quality issues. This presentation was originally prepared for the AASHTO Stormwater Summit and Workshop in September 2025, and it was also presented at the AASHTO Stormwater Working Group meeting in December 2025. My name is Alana Spaetzel. I'm a Supervisory Hydrologist with the U.S. Geological Survey's New England Water Science Center, and this presentation was prepared in cooperation with the Federal Highway Administration. In the presentation, we'll show how StreamStats, the highway runoff database, and SELDM may be used to answer questions about stormwater runoff quality, like where is the effect of highway runoff on receiving water quality likely to be greatest, and what proportion of stormwater constituent load is coming from roads in a watershed. We'll also provide information about the tool features and availability for StreamStats, the highway runoff database, and the Stochastic empirical loading and dilution model. For some background, the USGS, in cooperation with other federal or state partners, previously developed and currently maintains the geospatial web application StreamStats, as well as other water quality tools and datasets. StreamStats is widely used by state DOTs, as you can see by the figure on the left of this slide, showing the states in which DOTs have contributed to the funding of StreamStats applications. On the right, you're seeing a couple of examples of reports that USGS has developed in cooperation with state DOTs and FHWA to address questions about water quality and to explore the use of the stochastic empirical loading and dilution model. The three tools that we're talking about today have distinct features, although we will demonstrate how they can be used together. The core features of StreamStats are that it is used to delineate topographic drainage areas, estimate stream flow statistics, and compute basin properties. Commonly, those basin properties are driven by the properties needed for stream flow regression equations. StreamStats is implemented at statewide or even basin-wide scales, and that means that there are customized tools available within these applications. The highway runoff database is a data warehouse and preprocessor for the stochastic empirical loading and dilution model. It's used to retrieve event mean concentrations of highway runoff. It can be used to calculate statistics easily, and in particular, in its function as a preprocessor, it can be used to get the input statistics needed for water quality simulations. The highway runoff database is updated to reflect new data, and if you have data collected that would be appropriate for the highway runoff database, you can refer to our contact information at the end of this presentation for providing those data for future input. SELDM is a model. It's used to simulate stormwater flows, concentrations, and loads for constituents of interest, and it's used to identify the likelihood of water quality exceedances. SELDM is also available in some region-specific applications. This simply means that we've taken the SELDM application and updated with region-specific statistics. So now we'll turn our attention to the examples, and we'll take a look at two different ones today. The first I am drawing from work that Connecticut DOT is doing, and it is intended to address the question of ranking or prioritization of potential sites where stormwater management practices might be needed. So for this example, I've put together a selection of sites in Connecticut where a highway is discharging into a receiving water body. And this is already just a fraction of the number of sites that might be of interest, but it demonstrates that commonly there may be many of these sites, and it's helpful to have a way to narrow down where should time and attention be spent first? So where is the effect of the highway runoff on the receiving water quality likely to be greatest? So in this example, we are ultimately going to use SELDM to simulate the effects of the highway runoff on the receiving water. But in order to get to that point, we first need to get basin properties that are needed in SELDM to simulate the volume and timing of stormwater flows. SELDM is simulating long-term populations of runoff generating events, and so it's important that we can translate precipitation statistics into the amount of stormwater flow, as well as at what point or how much of that flow is concurrently being discharged from the highway and the upstream basin. So this figure shows sort of a hypothetical site where we've got a highway discharge and into a stream, and that stream, of course, has a drainage area that we call the upstream basin. So the basin properties that we need are the drainage area itself, the imperviousness, the main channel length, and main channel slope. And we can easily get those basin properties from StreamStats for the upstream basins. These properties also need to be obtained or estimated for the highway site. Conveniently, in StreamStats, there is an option to use a batch processor mode in order to do those upstream basin delineations for many sites at once. So if we're following along from the original map, we have those orange diamonds indicating locations where we want to do SELDM simulations, and we input those to StreamStats to get the basin properties, and then estimate the highway site characteristics based on information that the DOT already has, or estimates from maps, or from just based on representative highway characteristics that are known to the user. From there, we can use SELDM to actually simulate runoff at the sites using those site properties that we determined. And in this case, we're using the preloaded hydrologic and precipitation variables that are already in StreamStats. So for this example, we're not going to explore all of the inputs of SELDM. We're focusing primarily on those basin properties. So in SELDM, this image from the SELDM application itself, which is provided in an Access database and has these forms that you can use to step through and run a simulation. You do have the option of using a batch run mode as well, and that does require creating some input files, but there is support available for that if a DOT wants to explore that option. In the case of Connecticut, they have implemented the use of the batch processor. The upstream basin and highway site forms within SELDM show the input variables for drainage area, the main channel length and slope, as well as the imperviousness. So you can see that those characteristics that we draw from StreamStats can directly be input to SELDM. All right, so at this point, we've now run SELDM for all of those sites, I think around 90 or so from that original figure. But for the sake of this demonstration, we'll extract just a handful of those sites and talk about comparing them. So on this slide, we're seeing SELDM simulation results, which are, as I mentioned previously, simulated runoff events. And so what's associated with those events, the information associated with those events, is the highway runoff volume, as well as the upstream storm flow volume. And we're really concerned about those concurrent flows because, of course, if highway runoff is being discharged into a stream with very high flows, we would expect the dilution of that highway runoff and a dilution of the potential effects that we might see on water quality. So instead of looking at a particular concentration of a constituent, you can envision this figure could also be viewed with respect to constituent concentrations. But in the case when we were really trying to take a large number of sites and get a sense for, okay, where do I need to focus more attention because the highway runoff is a larger proportion of that downstream flow, using a dilution factor can be a really valuable approach. So that is the variable that we're showing in this case, and the dilution factor is on a scale from 0 to 1, and 1 means really there's no dilution. It means all of the downstream flow is highway runoff. So that's what this little equation here is showing, is that highway runoff volume divided by the highway and upstream storm flow volume. Those two elements together create our downstream flow, gets at our dilution factor. So with all of that, let's get into how might we rank these. So we have over 1,000 simulated events for each of these sites. So we're going to just kind of draw 1 point for comparison, and that blue line is placed at the 0.5% exceedance probability, which in the case of southern New England, based on the number of storm events per year and the total number of events that were simulated, that approximates about a 3-year exceedance risk. So if we take those values at the blue, at that 0.5 percentage, we can then look at the dilution factors associated with each site, and we can rank based on those dilution factors. So I've just designated these sites A through F, and if we look at the dilution factor associated with that 1 in 3 year storm event, we can then rank on which one is greatest. So remember that a dilution factor close to 1 means that we're expecting a pretty large effect of the highway runoff on the receiving water, because a very large proportion of the downstream flow is actually the highway runoff. So with that, we can then, based on those rankings, we can move towards understanding which sites might need or might be most susceptible to these highway runoff water quality effects. So now we'll turn our attention to a different example, which is to think about, if we're concerned about the total load of a constituent in a watershed, but we need to understand, well, what proportion of that load is actually coming from roads, and this is particularly valuable within TMDL development context. So for this example, we're looking at a basin in Rhode Island, and we're going to start again by going to StreamStats and getting information about our basins of interest that we want to have SELDM simulations for. And in the case of southern New England, we actually worked with state DOTs to add the number of road crossings, the length of roads by road category into StreamStats, as well as of course, the hydraulic variables and other properties needed to run SELDM. So this is showing just an example of what those basin properties look like in StreamStats. And so this, if you recall from the earlier slides, that StreamStats has the ability to be customized in the sense that we were able to add these kinds of road characteristics even though they are not directly input to a streamflow statistics regression equation. So we first use StreamStats to delineate the watershed, and we determine both the impervious area and the highway area within this watershed. And we can do that by getting the length of roads by road category, and with a known road width, we can use both that road width and the road length drawn from StreamStats to get at a total area of major road impervious area. And in this case, that's 876 acres in this watershed. And just a reminder that the roadway properties are they're not widely available, but they can be added to StreamStats through a cooperative agreement with USGS. All right, so in this case, we are using SELDM to simulate the long-term mean annual yields of total nitrogen from these planning level analyses of highway and urban runoff. And the examples shown here are from the Southern New England work that we did. So these have already been developed, but they could be developed in other places. But essentially, this is relying on highway runoff data from the HRDB, and then to get the urban runoff or the urban load of the total nitrogen, we looked at input. We looked at BMP inflow data in the International Stormwater BMP database, and we used those to do SELDM simulations and get at the long-term mean annual yields of total nitrogen. So this figure is showing for both highway sites and urban sites what those annual yields are. So for the case of highway, that's about 9.5, and for 9.5 pounds per acre per year of nitrogen, and then for urban impervious area, that's 11.9 pounds per acre per year. So now we have these yields that can be applied to areas in the watershed. So we take the area of the major roads, and we multiply that by the total nitrogen yield that we simulated using SELDM, and we can get at a total long-term average annual load of nitrogen from the major roads. And then we can do the same process applying that to the urban impervious area, so non-roadway urban impervious area, and multiplying that by our average annual yield. And as you can see, for the watershed that we are doing these calculations for, the other impervious areas, so the non-roadway, contributed that 96% of that total nitrogen load. And we found this to be true across a number of watersheds that we simulated for. So the purple box is indicating the Pawtuxet River, which is what this example specifically showed. And all of these basins in this case are tributaries to the Narragansett Bay in Rhode Island. And so overall, the percent of the highway runoff constituent load for total nitrogen was about 3.6% overall for all of these tributary totals. So again, we can repeat this analysis. We can do this for other tributaries and get a sense for what proportion of the total nitrogen stormwater runoff load is coming from roadways, which can be really helpful information, again, for the development and response to TMDLs. So just a quick recap, using SELDM with the inputs that we were able to get from StreamStats and the highway runoff database, the two examples demonstrated ways that we can help prioritize attention for management strategies based on risk for adverse effects. And it also helped us understand the relative contributions of constituent loads from developed sources, and again, provide input on TMDL development. I want to wrap up by looking at the availability of SELDM basin properties in StreamStats. So these are the basin properties that were mentioned earlier that we do need for SELDM simulations. That's drainage area, main channel slope, main channel length, and imperviousness. And the availability of these characteristics does vary. These green states have all of the characteristics that are needed, and those with the letter R also indicates that there's that roadway information. So you'll notice, of course, that the southern New England states, Connecticut, Massachusetts, and Rhode Island, have these properties and the roadway information, and that was done in the past couple of years as part of work with these states and the Federal Highway Administration. The Highway Runoff Database also has kind of a variety of representation across the state and across the states. It is being, it is updated. So if there's new data here that could be added, that's definitely something that would be great for folks to reach out to the USGS SELDM team to provide that data for future use. But you can see here we have 280 sites represented in the database. Those are from 43 data sets, and this amounts to nearly 120,000 event mean concentrations in this highway runoff database. Finally, these examples were not explored in a high level of detail, and so if you want to get more information about an example that was seen in this presentation, you can read more about the use of SELDM at our webpage, usgs.gov/SELDM. All reports and the software itself are available there. There's also, of course, the option to just reach out to us directly. My contact information is on that SELDM webpage, but we also have a SELDM inbox you can reach us at.